Greeting everyone. I surely say that most of you guys might have their laptop or computer. Moreover, don't you know that each computer will have the processor or CPU, which is the logic circuitry that respond to and process the basic instruction that will drive a computer. Therefore, in this video, we are going to talk about how the pipeline of processor is designed. However, there are also have many types of processors, but today we will mainly focus on and we will only discuss about processor Intel microarchitecture Skylake Core i7, which is released in August 2015. Before we start, some of you may have no idea what the meaning about pipeline. So let me briefly explain what it is. Pipelining is the process of storing and prioritizing computer instruction that the processor executes. The pipeline is a logical pipeline that lets the processor perform an instruction in multiple steps.
When we consider the designs of sophisticated, dynamically scheduled processor, the designs of the functional unit, the cache and register file, instruction issue and overall pipeline control become intermingled, so making it difficult to separate the data path from the pipeline. So because of this problem, many engineers and researchers have adopted the term of microarchitecture to refer to the detailed internal architecture of a processor. The Intel Core i7 uses a schema for resolving anti-independent and incorrect speculation that use a reorder buffer together with register renaming. Register renaming explicitly rename the architectural register in a processor to a larger set of physical registers. So the Core i7 uses register renaming to remove anti-dependent. Register renaming requires the processor to maintain a map between the architectural register and the physical register. Indicating which physical register is the most current copy of an architectural register. By keeping track of renaming that have occurred, register renaming offers another approach to recover in the event of incorrect speculation. Simply undo the mapping that have occurred since the first incorrect speculated instruction. This will cause the state of the processor to return the last correctly executed instruction, keeping the correct mapping between the architectural and physical register.
Let me introduce you into Skylake microarchitectures. It is a groundbreaking innovations in the world of computing, offering a plethora of enhancements aimed at revolutionizing performance and efficiency. Let's dive into its key features and how they elevate the computing experience. Apart from that, you can look at the pictures while I'm describing. For the first one, this is an amplified capacity. Skylake boosts larger internal buffers, which expand the workspace for builder. This enables deeper output orders as well as triple O executions and heightened cache bandwidth. For the second one, it is a streamlined front end. With an improved front end throughput, Skylake accelerate the initial state of processing. The next one is the third one. It is smarter decisions making. Enhanced branch predictions capability empowers Skylake to make smarter guesses about the next step in computations. For the fourth one, efficient arithmetic. Skylake's optimize arithmetic operations resulting in improved divider throughput and latency. For the fifth one, it is an eco-friendly design. Lower power consumptions ensure sustainable operations. The sixth one is a collaborative performance. Skylake supports simultaneous multi-threading as known as SMT through hyper-threading technology, enabling efficient collaborations between multiple processors and teamwork in constructions, where tasks are divided among collaborators for faster completions. The seventh one is a versatile functionality. Skylake achieved balanced floating point arithmetic, ensuring consistent performance across various computation stacks, such as at multiples. The microarchitecture supports flexible integrations of multiple processor core with a share and core subsystem consisting of numbers of components, including a ring interconnect to multiple slice of L3 or an offline L4. This is an optional. Also, it is a processor graphic integrate memory controller interconnect fabrics and moreover. Lastly, a 4-core configurations can be supported similar to the arrangement. Next, I am going to discuss about the front-end efficiency. The first one I'm going to talk about legacy decoding. Skylake front-end delivered an impressive 5 micro-operations as known as UOPS per cycle to the instruction decode queue as known as IDQ, enhancing processing efficiency by efficiently decoding instructions. The next one is the optimized resource management. The instruction decode queue expand capacity coupled with the loop stream directors and known as LSD, enable efficient resource management, ensuring uninterrupted executions of tasks. The next one is the enhanced predictive ability. Skylake's improved branch predictor, enhance predictive accuracy, and minimize computational delay. In summary, Skylake microarchitectures represent a quantum leap in computing technologies, offering unparalleled performance, efficiency, and versatility. Whether it is powering high-performance servers, driving immersive gaming experience, or enabling cutting-edge scientific research, Skylake stands as a testament to human ingenuity and innovations in the digital age.
As you can see here from this picture, show the overall organization of Core i7 pipeline with the memory component. The Skylake microarchitecture built on the success of the Harshwell and Bordwell microarchitecture. We can see that there are 14 states in entire pipeline with branch misprediction costing 17 clock cycles, and this design can buffer 48 loads and 32 store. The execution of a ready micro can start simultaneously in each of the 6 distinct functional units. Starting with the first one, instruction fetch. The processor uses multiple level branch target buffer to achieve a balance between speed and prediction accuracy. There is also return and address stack to speed function return. And the second one is the 16 bytes are placed in the precoder instruction buffer. The precoder state transforms the 16 bytes into individual instruction. This precoder is non-trivial since the length of the instruction can be from 1 to 15 bytes. And the precoder must look through a number of bytes before it knows the instruction length.
The third one, micro-op decode. Individual x86 instructions are translated into micro-operations or micro-op. 3 of decoders handle x86 instructions that translate directly into one micro-op. For x86 instructions that have more complex magic, there is a microcode engine that is used to produce the micro-op sequence. It can produce up to 4 micro-op every cycle and continue until the necessary micro-op sequence has been generated. The micro-op are placed according to the order of the x86 instructions in the 28-entry micro-op buffers. For the fourth one, the micro-op buffers perform loop stream detections if there is a small sequence of the instructions which is less than 28 instructions or 256 bytes in length that comprise a loop. The loop stream detectors will find the loop and directly issue the micro-op from the buffers, eliminating the need for the instruction fetch and instruction decode state to be activated. For the fifth one, perform the basic instruction issue. It is looking up the register locations in the register tables, renaming the register, allocating a recorder's buffer entry, and then fetching any result from the register and reorder buffers before sending the micro-op to the reservation stations.
For the number 6, the i7 user 36 entry satellite reservation station. It is shared by 6 functional units. It is up to 6 micro-op and maybe be dispatched to the functional unit every clock cycle. And for the number 7, the individual function unit execute micro-op and then results are sent back to the any waiting reservation station as well as to the register retirement unit, and where they will update the register state, and once it is known that the instruction is no longer speculative, the entry corresponding to the instruction in the reorder buffer is marked as some piece. For the number 8, when one or more instructions at the head of the reorder buffer have been marked as complete, the pending write in the register timing unit are executed, and the instructions are removed from the reorder buffer. And moreover, hardware in the second and fourth step can combine or fill operations together to reduce the number of operations that must be performed.